All right. Hello, guys. Welcome back. Um, we're finally into the chapter on integrals. So in this first section, we're introducing the definition of double integrals and the definitions for a double integral in particular over rectangles. We'll be dealing with more general version of integration afterwards, like integration on say, a circle or a triangle or different domains. But today we're learning on rectangles. So let me first give some motivational pictures. This is from Stewart. So basically, this is how integration in say two-dimension works. So if you have a surface and you want to calculate the volume under this surface under some rectangular domain, then the idea is quite simple. You cut the rectangular domain into several pieces. You calculate the height. The height can be determined by some value within that domain, and then you add up the volumes of these rectangular objects. And by cutting the domain, the rectangle or square, finer and finer, you'll get almost the correct volume of the surface. So that's basically how we construct the integral. Now let's go back to the definitions, and let us do this slowly, because integration theory is a little bit more, actually, like a little bit different from differential theory. So first of all, let me introduce what is a partition, what is a grid, and what is a mesh. So in this particular section, we'll be focusing on this type of domain, AB and CD. So AB is basically the interval between A and B, and CD is the interval between C and D, where the product is simply a square, a rectangle. So it is a rectangle that looks like this, AB and CD. Okay? We're in this section in particular interested in this kind of domain. So as I mentioned, we want to cut the domain to be a bunch of collection of grids, right? So we define a grid defined by G is given by these following notations. Say P is a partition for AB. So that means that we collect a bunch of points within A and B. For the first point, x naught, we define to be A, and for the last point, xn, we define to be B, and we find a bunch of points in an intermediate. So x naught all the way to xn, n can be so large. Similarly, for CD, we have Q, which is another bunch of numbers, where the first guy, y naught, is C, and the last guy, ym, is D. So this partitions actually cuts the rectangle into several little rectangles. And we give some notation. Our ij here is defined to be xi minus 1 xi times yj minus 1 yj. So that is basically a small rectangle within the big rectangle AB times CD. So these are so many notations. Let me go through some examples. For example, if I partition this 17 times 03 into this grid 1247 and 013, then we chop the rectangle vertically at 1, 2, 4, 7, horizontally at 0, 1, and 3. And you get this many of little rectangles, right? For example, in this case, this is called R11, and so on and so forth. So basically, this Rij are rectangle that is the components of this large rectangle. And the idea of integration is to make this small rectangle finer and finer to approximate the actual volume under a surface. So yeah, apologies for this. There's more rotations. For convenience, we denote the delta xi by the length of the interval xi minus 1. So for instance, delta x1 will be 1, delta x2 will be 2, and delta x3 will be 3, where delta y1 is 1 and delta y2 is 2. So that is how we define the length. And finally, we define the mesh, which is the largest volume of the rectangle. So note that the volume, actually the area for the rectangle is defined to be delta xi, delta yj, That is the usual definition for rectangular area, right? Delta xi times delta yj will be the area of Rij. So in this case, the mesh of G, the grid, is given by this big block, 6. So in this particular case, the mesh G will be 6. So let me go through the definitions again. Basically, a grid G is simply partitioning the rectangle omega here to be a bunch of little rectangular areas, where each rectangular area have the x component being xi minus 1 xi, and the y component yj minus 1 yj. Where in particular, we define the the mesh of the grid G to be the maximum area or maximum volume of this grid G. Okay, so yeah, those are the 6 rectangular areas, and we find the maximized one, which is 6. Now, after this partitioning type of definition, we can start defining a Riemann sum and Riemann integral. So I want to mention again, the important part about this lecture is on the practical examples and how you can evaluate the differentiations and integrations. So these are just for completeness, but they're obviously kind of important in the sense that if you understand how this is built up, then you know why calculus is kind of fascinating, because these concepts are not really that obvious in some sense. Okay, so that does carry on. So for now, let us given a grid G. So G is basically a product between a bunch of points within A and B and a bunch of points within C and D. So now the idea of Riemann sum is that on some particular grid, a small grid here, we find an arbitrary value, an arbitrary point actually, to evaluate the function f of xy. So a choice of point here, gamma, is given by this notation. Sorry, there's a lot of Greek letters going on. So this is pronounced Kc, and this is pronounced eta. So Kci eta j is basically some points that is within Rij for every I and for every j. So we're choosing a two-dimensional point in a grid to evaluate a function. Basically, if you have a grid, then what you have to do is to find the height, right? And the height can be evaluated by using this particular choice of points. And what we want to show is that the integration actually does not depend on the choice of point, because you can sort of visualize this. When a grid gets smaller and smaller and smaller, then that particular choice of points actually concentrates to a finer region, right? So the choice of points should not give us any different consequence on the integration. So now we have 3 components: a function f defined on A, B, and C, D, a grid G that partition A, B, C, D, a choice of points, a collection of points that lies within Rij for every I and j. Then basically we can define Riemann sum with these 3 components, f, g, and gamma, to be this summation. So again, this is actually really, really intuitive in a sense that delta xi, delta yj, taking product of these 2 guys is basically the area for the grid, right? And to find out the rectangular volume, you have to multiply again by the height. Where in this case, we evaluate the height by some particular point within the region Rij. So again, using this graph, you can see that we have a particular small rectangular region, and we choose some point, evaluate its function value, and we multiply it by as a height. And then we can get the volume for that rectangular region, right? For that solid. So this is a particular Riemann sum with respect to this function, this grid, and this choice of point. So as I mentioned, the idea of Riemann integral is to try to cut the grid finer and finer to approximate the actual surface, actual volume. So this is where the mesh notation comes in. If whenever the mesh goes to 0, so we cut the interval to be so small that the maximized rectangular area is so small, then this pi converges to L for some number L, then we say that f is Riemannian integrable. So in particular, that is saying that for every epsilon, again, this is an epsilon data definition. I know we have encountered this in like chapter 14.2, and this is all, I think this is almost the last time we can see this. So for every epsilon larger than 0, we can always find some threshold delta so that these two guys are so close whenever the grid G is so small. And that result is independent of the choice of gamma. So we are saying basically that given a G, the grid of AB cross CD that is so fine that the match of G is less than delta, then whatever choice of point, whatever point you choose in a grid, the total volume of the Riemann sum is actually close to some number L within a threshold of absolute. So by cutting the grid finer and finer, you'll get the limit of this being L. If that L exists, then we say that the function f is Riemannian integrable on the rectangle area ABCD. And in particular, we denote the L by this notation, a double integral, and this area omega f of xy dA. Okay, this is kind of intuitive from our previous notation on Riemann sum. So this is a double sum here, right? A double sum, and you have the height f of xy, but you have the base area dA. dA is delta xi, delta y, delta yj. Sorry. Okay, so I know there's a lot of notation going on. Basically, Riemann integral obtained as the following way. For a rectangle area, we first cut it into a bunch of rectangles, small rectangles. We chose some point within that each rectangle. We evaluate the function value of that particular point as serving as the height of that object, of that solid. And then we sum up the volume obtained from multiplying the length and the width of this small rectangle area with the height given by the choice of point evaluated in the function. So we have now a bunch of volumes. Add them together gives you a Riemannian sum respect to this grid and this particular choice of point. If when a grid goes finer and finer, this number, the Riemann sum, actually converges to some particular number L, then we say that the function f is Riemannian integrable, and that this L is called the double integral of f over this area A. And this actually represents the actual volume of what we're imagining. So this guy, basically, the volume below a particular surface. Okay, so that's a lot. Let us do some examples. So this example will not be on quiz. It is just a conceptual example. So again, we see that we're back to this example. We cut 1,7 times 0,3 into this region, 1, 2, 4, 7, and 0, 1, 3. So there will be 6 rectangle areas. And now we choose this points, say 3 half, 1 half in the first rectangle area, a square actually, and 2, 2 on the boundary of this rectangle area, and so on and so forth. There's a bunch of points here. You can see that the boundary and the corner can actually be chosen. We're simply choosing everything in this block. So the boundary is also contained in that block. And then the Riemannian sum of f with respect to this grid G and this choice of point gamma is given by, say, f22 times the area here, which is 2. So you have this volume, and you have those 6 different volumes, like a pyramid. After adding that up, you'll get something like 172.25. So this will be a rough estimate of the actual volume, which we will see later. It is a little bit off, but it is close enough somehow. Okay, so now let us try to show somehow that this. Oh, sorry, I think I didn't. Oh yeah, sorry, I didn't mention the function. F of xy is defined to be xy. So in particular, say we're choosing 2, 2, then the function value will be 2 times 2, which is 4. That'll be the height of this particular solid. Okay, so and then you can do the algebra and you get 172.25. So now, let us try in some sense to approximate the correct value of this solid, the volume of this solid. So the idea is as follows. We want to cut the region from 1,7 and 0,3 finer and finer, right? So say we choose a uniform type of way to cut the region. We cut this thing into n pieces, and also this thing into n pieces. So for example, what is the next point after 1 in this particular partition? The length of each small interval should be 7 minus 1 divided by n, right? So that is 6 over n. So next point after 1 will be 1 plus 6 over n. Similarly, the next point over that point will be 1 plus 6 over n times 2, and so on and so forth. So we see that we can partition 1, 7 into these small points. 1 plus 7 minus 1, which is 6 divided by n, I, where I ranges from 0. So you can see that when I is 0, then this is 0. So it corresponds to the first point 1. And when I is n, then the n and n cancels out. So you have 1 plus 6, which is 7, which is the end point, right? The same thing happens for the vertical region. So yj can be defined as this same thing. We sum out from 0, and you want to sum all the way to 3. So you're summing up 3 divided by n times j. When j is 0, you have the bottom point 0. When j is n, you have the upper point 3. So this is a grid of this rectangular area that the mesh goes to 0 as n goes to infinity. So we're cutting more and more pieces of the rectangle. So now let us try to estimate this particular integral. So in a small region is Rij. So we have x, the left bottom corner is xi minus 1, yj minus 1, and you have this corresponding 4 corners. This is a particular grid, Rij. Let me mention it here. It's Rij. And we see that our function has a particular interesting property, that is when x and y are larger, then this function is larger, right? This is increasing in x and y, basically. So we know that within this grid, the maximized function value of f will be at this point, and the minimized function value of f will be at this point. So for every particular xy in this grid, we always have this inequality. F of xi minus 1, yj minus 1 will be less or equal to f of xy, will be less or equal to f of xi, yj. Now, how is that useful? So this is useful. This is useful in the sense that xy is an arbitrary point, right? We cannot really evaluate it. However, xi and yj, these are given. These are given in particular formats. So we can do some evaluation. So we see that by summing this up over each grid, we have a Riemann sum for any Riemann sum. This gamma n is a particular choice of point within the grid Rij. But we know that that does not really affect our formula here because we always have the maximized version and a minimized version of choice of points. So on the right-hand side, you have f of xij, f of xi, yj, times delta xi, which is 7 minus 1 divided by n, and delta yj, which is 3 minus 0 divided by n. The same thing happens for the left-hand side. So now let's try to evaluate the left limit and the right limit of this guy. So we see that for this guy, this two thing is actually independent of I and j. So you have 6 times 3 in the numerator and n squared in the denominator. For the summation, we know that it is xi minus 1 product yj minus 1, right? That's the definition for f of xy. So in particular, xi minus 1 is given by 1, starting from 1, plus I minus 1 many 6 over n. And the same thing happens for yj minus 1. So note that the summation here can be split up because this guy is independent of independent of j, and this guy is independent of I. So we can split the summation into summing over I and summing over j. In particular, this is simply summing from 0 to n minus 1, right? That is a arithmetic progression. And based on your junior or high school math, we know that the formula of that is given by n times n minus 1 divided by 2, where summing over 1 gives you n. The same thing happens here. So this is a constant, where this guy is given by the formula n times n minus 1 divided by 2. So now if we move the n squared inside, you get that the first guy, so n squared inside with this divided by n, and this divided also by n, then this guy will become 1 times 6n, you divide this by 3, so you get 3n minus 1 divided by n, where latter term is simply 3n minus 1 divided by 2n. We see that when n goes to infinity, this goes to 1 and this goes to 1. So the whole thing becomes 18 times 4 times 3 half, which is 108. Okay, let's see if we have a matching upper bound. So actually everything behaves the same. The only difference is here. We're summing from I from 1 to 1 to n instead of from 0 to n minus 1. So the formula becomes n times n plus 1 divided by 2 and n plus n plus 1, n times n plus 1 divided by 2. Which, again, by moving the n inside and taking n to infinity, this guy still converges to 3, and this guy still converges to 3 half. So the eventual number is still 108. We can see then by squeeze theorem that this goes to 108 and this goes to 108 as n goes to infinity. And so this must go to 108, independent of the choice of gamma n. So we somehow show that the integral should be 108. But let me emphasize this. This is a very, very special kind of choice of grid, right? We actually partition the grid uniformly. But as I draw here, this is in particular not a uniform grid, right? You have a different length of the intervals on the x-axis and the y-axis. That would not be a big problem. So as I mentioned here, we can always show that that particular grid still converges to the value 108 that we just compute, because you can choose a finer and finer and finer grid. This Pn and Qn, finer and finer, that grid is in particular finer than the grid that we just chosen. So by comparing those two grids, the uniform one, which is very, very fine, and the arbitrary one, which also is fine, then by comparing those two guys, you can show that actually the arbitrary one also converges to this number 108. So then we can conclude that the double integral of this function xy over the region 17 times 03 is indeed 108. However, obviously, this is not a very good kind of arithmetic, right? We cannot perform this type of algebra every time. It is too troublesome. And this is already a very simple function. If we're dealing with something that includes transcendental function, like exponential functions, sine functions, or log functions, then it'll be very difficult to compute this type of summation formula here and here. So it is very crucial for us to find a more systematic way to compute the integral, provided that the function is integrable. So lastly, sorry for this. Lastly, let us mention that, so basically the integration can be considered as a volume under the graph z equals f of xy. So this is a graph, and we're interested in the rectangular region here. So it looks like this. And now I want to find the volume. The volume is given by this double integral. Okay, so back to what we just mentioned. It is in general very difficult to evaluate the integral and even to check integrability. So we don't know which functions are integrable or not. But this next theorem tells us that continuity actually is the key. Whenever a function f is continuous on this rectangular space, then it is integrable. So basically that means that we can choose any points and any grid. It all converges to the same value, the remain double integral. And this is in general kind of hard to prove, so I will show that in a supplement file, which is again not really important, but you just have to know that continuity implies integrability. So in some sense, we learn this type of notion of properties of function in a progressive way. We know that differentiability is very strong, it implies continuity. And integrability itself, sorry, did I say that 2 times? Differentiability is very strong, it implies continuity, and continuity implies integrability, meaning that integrability is sort of the weakest type of condition. Everything almost implies integrability. So it is more general that you can integrate a function in comparison to you can differentiate a function. Okay. I have this small, not really important remark here, is that actually we can characterize every possible integrable function. So it turns out that even continuous functions are integrable, but integral functions can be not continuous. And there is a very simple example here. So if we set up the functions, that function f of xy, f of x to be 1 on region of 0, 1, and 2 on region of 1, 2. So the graph looks like this. This is 1, this is 2. And, oh, sorry, my bad. This is 1, 2, 1, 2. Okay. So it is 1 within this interval and 2 within this interval. Now we know that you can integrate this, right? By direct argument. This is 1 and this is 2. So the integral over this interval 0, 2 should be 2, right? 1 plus 2. And 3, sorry, it should be 3. So obviously this function is not continuous at the point 1, right? However, the discontinuity is actually just that point, right? It is actually continuous within the region 0 and 1 and 1 and 2. The only discontinuity happens at 1. So that is the kind of condition for integrability. We can actually show that a function is integrable, is Riemann integrable, then it must be continuous almost everywhere somehow. The almost everywhere has an actual meaning, but we will not go further here. So yeah, basically what we have to know is that the most of the functions you can see here, which is continuous, are integrable. So you can do the integration without any hesitance. Right. So we are finally finished with the conceptual definition of integrability and Riemann integral. Now we're into the practical computational version. So the first, actually, maybe the last theorem for this section is Fubini's theorem. Fubini's theorem tells you a way to compute the double integral in terms of iterated one-dimensional integral, which we are very familiar from calculus 1. So now, given a function f on AB times CD, a rectangular region, which is continuous, then the double integral, which is defined in that very complicated Riemannian integral language, can actually be computed by this iterative integral. So we can first compute f of xy on the x component from A to B. Then after evaluating, you have a function in terms of y, right? And we can then compute the integration from C to D respect to y. The same thing happens for if you compute from C to D first respect to y, and then A to B respect to x. So let's reduce the two-dimensional double integral problem into a one-dimensional integral problem, which should be very familiar with. So you can evaluate double integral using this method. Okay, now let me try to show this. This is actually quite simple. This is a simple estimation on both sides. So again, we start from a grid. So if we're given a grid, which is a grid of AB times CD, it is a bunch of points, x0, x1, all the way to xn, y0, y1, all the way to yn. Then we know that by extreme value theorem, if you're not familiar with this, please go back to 14.7. So basically it is saying that a continuous function can always achieve its maximum or minimum value at a closed and bounded set. So in this case, we are dealing with a rectangle, which is obviously closed and bounded. So you can find some point Ci eta j, Ci bar eta j bar. Sorry, I'm out of notation, so I use this weird notation within this rectangle region Rij, so that it is the maximum over all points within the rectangle. So fxy will be always less than f of Ci bar eta j bar whenever xy belongs to Rij, and also f of Ci eta j will always be smaller than f of xy whenever xy belongs to the rectangular area region. So now let us integrate these functions. So actually these two guys are constant function, right? That is, they are just maximum value, minimum and maximum value on the region xi minus 1 xi times yj minus 1 yj. So by integrating respect to x in particular, in this case, we get the middle term is simply the one-dimensional integration, and that the left-hand side here is actually this guy times xi minus xi minus 1. So that's the interval delta xi, the interval length. Similarly, right-hand side is simply f of Ci bar eta j bar times delta xi. So observe that here I only integrate respect to the xi minus 1 to xi. And now we sum over 1 all the way to n, I equals to 1 all the way to n. So this is basically summing up every small region of integration from x naught, which is a, all the way to xn, which is b. So you have this a to b f of xy dx. Where on the left-hand side, I didn't change anything. I just sum it up. And right-hand side, I also sum it up. So now this after integration is actually a function of y, right? And it is obviously continuous in y, so that it is integrable in the one-dimensional sense. And now, let us do the integration again with respect to from yj1 to yj, and then you can get a delta yj here, right? Because it is again a constant function. And summing over j from again 1 to m, you have the double summation of this guy and delta xi delta yj is less or equal to the iterative integral of this function and less or equal to this double summation, where you can see that this is actually a Riemann sum, right? We're summing up the volume given by the area of the grid and some particular height, where in this case, it'll be the least height in the region Rij. And this will be the max height in the region Rij. So by integrability, we know that f is integrable, right? It is continuous. So we know that whatever gamma and gamma bar here is, actually when the match G goes to 0, then the left-hand side and the right-hand side always converges to the actual double integral. So by squeeze theorem, the middle term here, the iterative integral, must be the same as the double integral. And you can prove the same thing for if you do the integration with respect to y first. So let me sort of help you guys on this theorem again. It basically tells us, actually, I think I write it down here. Yeah, it basically tells us two things. First, from the computational aspect, we know that we can compute double integral or even higher triple or 4 or 5 more integral via iteratively compute the one-dimensional integral. So if you're working with a rectangle, then we can compute the x coordinate first and the y coordinate. And also, this theorem tells us a really nice type of condition is that the order of integration is actually inconsequential. We can do the x integration first and then y, and it'll be the same value as the y first and then x. This will become particularly useful because some of the functions are really hard to integrate in one variable. But after change of the order, you can actually do the integration. We will see more example in the next chapter. So let me see the time. Okay, so maybe let me go through a particular example, which is what we have done before. So now let us integrate this function f of x equals to xy over the region omega, where omega is given by the particular rectangle that we have mentioned before, 1, 7 times 0, 3. So we have mentioned before, we have like two stage of computation. The first stage shows us that Riemann sum is 172.25. The second stage shows that if we choose a particular uniform partition of the separate intervals, then the limit actually converges to 108. So now, based on this theorem, we know that xy is continuous, so it is obviously integrable. The integral should be 108. And let us perform the algebra here. So by Fubini's theorem, we know that this can be computed using iterative integral. So let us compute the x first. Y here is just a constant. Just like taking partial derivative, we are doing partial integration somehow. We regard y as a constant when you are integrating with respect to x. So y gives here, and the integral of x, the antiderivative of x is simply x squared divided by 2. Plugging in 7 and 1, you get 49 minus 1 divided by 2, and that's 24. The integral of y over 0, 3 is simply y squared over 2, plugging 3 and 1, which you get at the end of the day, 108. So I would like to mention something here. First of all, this actually matches up with our previous computation, right? So the previous computation is actually doing in a really painful way. We compute the Riemann sum, and then we try to show that Riemann sum actually converges to some number, which is 108. And in this particular case, we compute the integral using the Fubini theorem. Fubini tells us that you can compute a double integral via iteratively computing one-dimensional integral. And lastly, I want to mention that I would be very appreciated if you guys try to use this notation. So because now we're doing multiple integration, it'll be wise if you keep writing down what variable are you plugging in. For example, I'm plugging x here, so I write x from 1 to x equals 7 instead of 1, 7. It'll be kind of confusing. And similarly, when I'm computing y, I'm going from y equals 0 to y equals 3. We don't want to write 0, 3 because it is, again, confusing. So yeah, be careful with those. So I think this is a good point to stop because there will be more computation afterwards. And we have now ended the conceptual part, which is the definition of the Riemann integral. So let me go over again what we have done now. We define a particular grid and the choice of point and the mesh for some rectangular region, AB times CD. And then with that type of information, with a function, with a grid, and with a choice of point, we can compute the Riemann sum, which is basically multiplying the area of the grid, Rij, together with the height, f of Ci, Aj. So you get this volume of this solid. And by summing this volumes up, you can get the approximation of the actual volume of the solid below the surface z equals to f of xy. And suppose that the limit when the mass of G goes to 0 actually converges to some number, then we will denote that number by the double integral. And after those fancy definitions, I claim that the continuous function is actually always integrable. And then those are conceptual part. Fubini tells us that, okay, now you can actually compute an integrable function, in this case, continuous function, via this type of iterative integration. You can compute the one-dimensional part first, and then do another one-dimensional part, basically breaking 2 into 1 plus 1. And Fubini tells us that it's valid. And we actually have already proven that this 108 matches up with our previous computation on Riemann sum. So that is all. And the next video will be kind of important in the sense that it'll be more close to what you'll be going to test in the quiz exams. So yeah, I will see you in the next video.